Welcome everybody to tonight's video on part 2 notes, the squeeze theorem and special trig limits. The squeeze theorem says that if you have a function, the f of x, and that f of x is between, the values of f of x is between the other two functions h of x and g of x, then that is a way you can find the limit. Because if you were to find the limit of h of x and the limit of g of x and they are the same, that means that f of x has to be that limit as well if it's between those two functions. So that's basically what that is saying, and it outlines the process. The process here, a 5-step process for using the squeeze theorem. Sorry, my computer. All right, so let's do an example here. So let's use the squeeze theorem to find the limit as x approaches c of the function, and we'll say c is 3, where it's between these two functions. So the first thing we want to do is rewrite the double inequality. All right, so that's step 1. Step 2 is we're going to take the limit of each function as it approaches c. All right, so then the third thing is then we're going to evaluate the end limits, meaning the limits of these two functions at the end. So notice if we put 3 in here, it's negative 0 minus 3 to the third plus 4, less than or equal to the limit as x approaches 3 of the function, less than or equal to between the limits, and we just have to put the 3 in here, sorry. So notice here it's 4, because actually when I put 3 in it gives you 0, sorry. Then you have the limit as x approaches 3 of the function, and this is also 4 because it's 0 to the third plus 4. So notice if the limit has to be between the two functions, a limit, and the limit of the two outer functions are 4, then that means the limit, put therefore, the limit as x approaches 3 of the function is equal to 4. So that is how you use the squeeze theorem. Now, what we're going to do next is use the squeeze theorem to help us solve limits involving trig functions. So when evaluating a limit with a trig function, you should first attempt to substitute, but then also if it's indeterminate, then you must use the squeeze theorem or some special trig limits which we will derive using the squeeze theorem. So using the squeeze theorem, if the squeeze theorem is needed, you will generally begin with a single trig function like sine x or cosine x set up as a double inequality between -1 and 1. And why would you use that for sine and cosine? Because that -1 to 1 is the range of those functions. So if you notice here, by direct substitution, find the limit as x approaches infinity of sine x, and notice that is dne, and the reason it's does not exist is because of the oscillating behavior. Between -1 and 1. So if we do the limit as x approaches infinity of sine x over x, using the squeeze theorem here, So we say it's between -1 and 1. So that means that's sine x. But we want sine x over x, so we're going to divide everything by x. And then we're going to take the limit of both sides as it approaches infinity. Sorry, I forgot to put the x there. All right, so now we can find the limits of the end functions. So -1 over infinity just goes to 0. And then the limit as x approaches infinity of 1 over x is also 0. So that means if the limit of this function has to be between two zeros, that means the limit as x approaches infinity of sine x over x is equal to 0. So now let's do the same thing with cosine. So cosine, notice we have it's between -1 and 1. We divide by x because our function is cosine x over x. And then we take the limit and then the limit as x approaches infinity of these functions. So this would be 0. And this side would also be 0. So that means the limit as x approaches infinity of cosine x over x is also 0. So let's try number 4. Why don't you, so the same thing applies. We're going to go -1 is between cosine x and 1. So now we're going to put x minus, so that means we have x plus 1. And then divide by x. Oops, sorry. So then we're going to divide by x. So we have the limit as x approaches infinity of x plus 1 over 1 is between the limit as x approaches infinity of x minus cosine x over x. All right. So, observing highest powers here, for this limit, we have, oh, sorry, it should be x, not 1. We have 1 over 1, so that's 1. And observing highest powers here, we also have 1. So therefore, the limit as x approaches infinity of x minus cosine x over x is equal to 1. All right, the next page helps us deal with the special trig limits. First, we use similar triangles. If this is theta, and this is a right triangle here, we'll call this the y coordinate. This will be 1 because it's in a unit circle. And this would be the x. And then here is also a right triangle. So we're going to use similar right triangles. We're going to say, if we use small over big, and noticing here's the big triangle, and this is theta, and this side here would be the tangent of theta. And then we have the sector, which if you go to here, it would be 1, 0. Also here would be 1, 0. And then up here, in this, which would be this point here, you would have cosine theta, sine theta. And then for the triangle right here, this point, endpoint is also 1, 0. These are all thetas, the angles. And this point would also be cosine theta, sine theta. So if you're using similar triangles, sorry, so that's what I did first in part 1, the large triangle. I used similar right triangles to get those pairs. The sector and the small triangle, I used the unit circle definition to get that ordered pairs. So double inequality using the symbols of the area of the small triangle, the area of the large triangle. Sorry, my computer froze. And the area of the sector, the relationship. So if we want to do that, we could say that the area of the larger triangle is going to be greater than or equal to the area of the sector, which is going to be greater than or equal to the area of the small triangle. So the small triangle is going to be the smallest one. So with a lot of algebra, we can find the limit, or we could find sine theta over theta, because remember the area of the first triangle is going to be 1/2 tangent theta, because remember area of triangle is 1/2 base times height. And then that's the area of the sector is theta over 2 pi times pi r squared. And then the area of the triangle, remember, is 1/2 AB sine theta. Well, in this case, it's just 1/2 1 sine theta. So when you keep going and doing some algebra, well, the radius of the circle is 1 because it's a unit circle. And then this would just be 1/2 sine theta. And then here you can cancel the pi's. So you have theta over 2 sine theta. And then if we multiply it by 2, we get tangent theta less than sine theta. And then remember, I'll just bring this up here, but tangent is sine over cosine. And then basically what you can do if you divide, or if you multiply it by you multiply everything by 1 over sine, then you get 1 over cosine and then take the reciprocal of everything, and there, but if you take the reciprocal, I gotta flip these inequalities, sorry. So that leads me to that sine theta over theta is between the cosine and 1. So now I can use the squeeze theorem to find the limit as theta goes to 0 of the cosine, and now I know it's between the cosine theta and 1. So basically I just use this inequality here that I created by similar triangles to find the limit of as theta goes to 0 of sine theta over theta. Well, the limit as theta goes to 0 of cosine theta is just 1, because cosine of 0 is 1. And the limit sorry, I forgot to write the limit here. 0 of 1 is 1 as well. So that means the limit as theta approaches 0 of sine theta over theta is equal to 1. So that's one of our special trig limits that we're going to use. And I'll make that the next video.